Okay, we should be live.
You are? Okay, bye.
Okay. Actually,
So shall I tell her we should be streaming live now?
yes, please do. Okay. So camera only does have the banner. If you want to turn that off, you can fade it. You can just do it here.
Just click right there?
Yeah, on the show. Actually,
Oh, okay.
duplicate.
No, no, I think it's better not to have so many different things. I think it's good to have a mechanism.
Oh, there we go.
Yeah. JD's the master of these things.
That works. Okay, so we've got just we want to focus on the display. If we want the display and banner, if you display plus the camera plus the banner. Um, where's the display and camera? Okay, let's put.
Yeah, I don't see that it added an extra thing there when you told it to do that.
It did. There we go.
Oh, maybe it was up at the front.
Yeah, it's up at the top. So,
Okay.
okay, so display only, display plus camera. Um,
See,
display only, display plus camera.
Apple.
Where?
Camera? Up. Up one.
This one too.
Oh, really?
No one else can see it, so I'm not too worried about it. Okay. So yeah, there we go. Okay. What did you do?
I hung a wet paper, well, he brought the wet paper towel, but I hung it on the door. And I think it's a humidity problem because when it got a little bit wet from the towel, though the towel wasn't on it, it started really freaking out.
Mm-hmm. Okay, so we'll do. Hello.
See how long it took you to notice.
I didn't know who it was, but I saw someone creeping this way. I saw you walking in the door. Yeah. How are you?
Good.
All right.
Rain didn't deluge as much as it was saying it was so far.
Hello.
Hi, how are you?
Good. How are you?
Good.
All right. Should we leave it at that? Okay.
If anything, JD, it's 2 deluxe.
All right. And where are we at? Oh, good. Okay. Yeah, give it a second because I'm just about. I'm going to just send a few people. the link directly.
So Stefan's going to be the one if some people there have questions, or does he have a live group with him, or is it all just streamed, like Zoom for him too? For her?
Pardon? Yeah, she's going off the live stream. I think that's all of them. All right. Okay, yes. So Stefan is, she's running it actually off the YouTube.
Oh, okay.
Yeah.
Well, I guess
All righty.
I got half-assed.
Okay. All righty. Well, welcome everyone. It's good to have everyone back. Yes, and thank you even more for coming out on this rainy day. So, for those of you who don't know, I'm Dr. J.D. Armstrong. Oh, Hayden, would you press record on the video camera? Oh, here, let me. One moment. It is right. All of us. There we go. Okay, we're going to start again. We're going to pretend I didn't do that, because I get to make how many mistakes in the introduction? Well, welcome everyone. It's good to have you all back, especially with the rain today. I'm Dr. J.D. Armstrong. I'm the Maui Technology Education and Outreach Specialist here at the University of Hawaii Institute for Astronomy. And one of the things that I sometimes do is put together these talks. And I'm really pleased to have Guy Jette come back and give another talk. For those of you who have been following the talks, he needs no introduction because you've done how many? Was it 6? This is number 7. Yes, and so, but for those of you who don't know, Guy spent 37 years with the Air Force. The last 15 of those were with the Air Force Research Laboratory and the Space Vehicles Directorate, so you can say that he is a rocket scientist. Okay. And, well, yeah, I had to. You guys, yeah, you know. He's currently affiliated with the University of Arizona. You're teaching some classes there, is that right? Yes, so some very lucky students. Let's all give him a warm welcome. So, yeah, and so.
Absolutely.
Okay. And
I guess this is probably close enough. Okay.
just drop it in pocket.
And then the lights, perhaps?
And then let's get
Drop the lights so we can see the charts. You don't want to look at me, you want to look at the charts. How's that, pretty good, everybody? Enough light? Too much light? Okay, well, welcome. First question I have, how many people have never been to one of my, I think this is number 7, one of the first 6 talks? Oh, you've never been here? And some of you have seen them, right? Okay. And the other question is, the first one I gave was actually 2013, 10 years ago. Anyone attend that one? It was on the observatories of southern Arizona. I thought maybe I should have given the same one. No one would have known. No difference, right? You did?
I think so, yeah.
Oh, okay, back in 2013. Okay, well, one thing I'm going to mention, I have like 60 plus charts. I mean, not 70, but 60 plus. It usually takes me an hour and a half to get through 60 plus charts. So I have a chart halfway through that says break, and we'll take a 5 or 10 minute break, so feel free to punch, i.e. leave. Or for that matter, I realize it's not early hour, it's late, it's raining, so if anyone has other things to do, no one's going to be upset if you don't, even if you leave while I'm talking. I won't feel the least bit offended. No one's taking names. So feel free to come and go, or go whenever you want, and you're not obligated to hang in here for the full 66 charts or 67 charts, okay? Okay, so with that, let me start. This is lunar geology, and the moon in a whole new light. And this is an interesting shot of the moon, because most of us look at the moon, we don't see that, right? We don't see the blue. It'd be kind of cool if we could, if we did. But this is basically highlighting some areas which we'll talk about, which are the mare. And these blue areas here, the way this was set up when they did this false coloring, there's large amounts of titanium and iron in these portions of the moon, unlike these portions over here, which are called the highlands, which we'll talk about too. So I thought it was a nice introduction chart. Oh, and by the way, I was gonna do Moon River, but that didn't seem appropriate. I couldn't find a good moon song. So anyone know what song this is before? Anyone recognize this song? Pardon? Moonraker, absolutely, from a James Bond movie. You know what year this movie was? I think it was 79. I looked at it this afternoon, but then I forgot. I think it was 1979. But anyway, but the problem is, I don't know what a moonraker is. I've Googled it several times, but I still don't know what a moonraker is. So if anybody has any ideas later, you can tell me what a moonraker is. Okay, first of all, let's start with some basic information. Here's the Earth, a little bit less than 8,000 miles in diameter. And of course, the diameter at the equator is a little bit larger by a couple dozen miles than it is at the poles. The moon is roughly, you can see here, 200 miles in diameter, so about 26% of the width or diameter. So you can say it's basically a quarter of the size in terms of diameter. The density of the Earth, 5.5 grams per cubic centimeter. And if you remember your high school math, a cubic centimeter is yay big. There are 2.5 centimeters in an inch. So that water is 1 gram per cubic centimeter. That's the kind of the standard. Our Earth is 5.5 on average. Okay, I guess that's okay. So 5.5, a lot of the surface rocks are in the 2s and 3s. Of course, our core is made of iron, so that's a little bit more dense. The moon's density is only about 3.3 grams per cubic centimeter. A little bit less, and we'll talk later about why that is, why the moon is less dense than the Earth in total. Now, one thing interesting about the Earth and the moon, of all the moons in the solar system, and I know that I used to say there was 179, but I just read recently there's 12 more moons they discovered around Jupiter. And so now we must have like over 200 moons in the solar system. But of all those moons, the moon, the Earth and the moon, we have the largest moon in the solar system compared to the planet that it orbits. So there's no other moon that's 1/4 the diameter of the primary it orbits, i.e. Jupiter, Saturn, whatever. So it kind of makes it to some degree the largest moon in the solar system in terms of what it orbits, okay? This chart is kind of cool. It puts it in perspective. We started out with Ganymede, which is the largest moon of Jupiter. I have kilometers here, but it's 3,300 miles in diameter. And Io, for example, is 2,300 miles in diameter, whereas our moon is 2,200 miles in diameter. And you go over here to Titania, we're talking 1,000 miles. So what's interesting, Ganymede and Titan. Titan is a moon of which planet? Saturn, largest moon of Saturn. So these two moons are larger than the planet Mercury. Kind of cool. And Callisto is next in line if you want to compare it to a little bit smaller than Mercury, and Io, then Europa. These three moons are called the Galilean satellites because Galileo, back in the early 1600s, with his little old telescope, looked at the moon and looked at Jupiter, saw these 4 moons. So they're the Galilean moons. They're the biggest ones of all those 92 moons that orbit Jupiter. Our moon then is basically, if you knock out Mercury, is number 5. So in absolute size, it's the 5th largest moon in the solar system. And we go out to Europa. We're a little bit larger than Europa. And Triton. Triton is the largest moon of what planet? Get extra points. It is the largest moon of Neptune. And a little bit tougher. And by the way, all these moons are bigger than Pluto. So that's why we kicked it out of the family, you know. And as a matter of fact, if we hadn't kicked Pluto out, its big moon is about half the size. So we could no longer say that our moon is the biggest moon compared to that's one reason we got rid of Pluto. Okay, and Titania, 1,000 miles in diameter, is from Shakespeare. You know what what planet Titania orbits? It's the largest moon orbiting Uranus. So kind of put that in perspective. Now, the other thing I should point out is we show the density of our moon like 3.3 grams per cubic centimeter. The only other of these moons that has a higher density, a higher cubic grams per cubic centimeter, is Io. Is a little bit more dense than our moon, but our moon's the second most dense of all the moons in the solar system, as far as we know. Okay, so far. This is an interesting chart. I know that most of us think of the moon, think of the Earth, and I can almost, if someone showed you a picture and they showed you the Earth and they put our moon at different distances, nobody would put it as far away as it is. Because look, you don't think of the Earth. There's the Earth, 8,000 miles in diameter, and then an average, our moon is an average of 238,900 miles away, okay? Or I like to round things up, 240,000 miles. That's how far away our moon is, and we could put all the other planets, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, between us and the moon. That's how much space there is. So the moon is really quite far away. Okay, this is a great shot because this shows what we're most familiar with, which is the near side of the moon. Okay, the side that we can see, basically. And this is the far side. So what we're going to talk a lot about is what's different about these. So here we saw these in blue because of the titanium and iron being pointed out. But these are mare, okay, M-A-R-E, which is Greek, or I think it's really Latin for seas. Because when early individuals, before they had telescopes, looked at the moon, boy, this looked like water. So mare is Latin for a sea. So that's why they're called mare. But what they really are, these mare, these are filled with basalt. The same kind of stuff we find here in Hawaii that comes out of the volcanoes. Okay, basalt is a basic igneous rock that's very common on the Earth, and it's on the moon too. And what happened here is there were a number, and we'll talk about specifically about some of these mare, but there were some large, and I won't even call them meteor strikes, they're really asteroid strikes many, many years ago, and they caused these large depressions, which then resulted in lava, or at the magma, it was called magma before it reached the surface, magma to rise and to fill these depressions caused by those last large asteroids, okay? Those are kind of like, if you're familiar with, we have several kinds of volcanoes. We have effusive volcanoes, like the Hawaiian Islands are considered effusive. We have these shield volcanoes, and we have, in the past, had large amounts, what's called the Deccan traps in India, and the Siberian traps in what's currently the Russia, the Soviet Union. Many, many millions of years ago, these were large amounts of lava flowed out into these large basins in Siberia and India. Kind of the same thing with the moon with these mare. So these then contrast with the rest of this, a lot different, very much lighter in color and not this dark basalt. These are called the highlands. And about 84% of the moon is made up of these highlands. And unlike this basalt, this is made up primarily of, if you're familiar with feldspar, the mineral feldspar, and feldspar is part of a rock that's called a northocite. And 84% of the moon is basically, this is considered the crust. Of course, this is crust too, but it's a secondary crust because of that lava. But the anorthosite covers 84% of the moon, and it's the same material. It's very common. It's not as common as granite and basalt on Earth, but anorthosite is very common on the Earth. It's also considered to be the primary material on Mars, anorthosite. So whether you go to the moon, whether you stay on the Earth, or you go to Mars, you're going to find basalt, you're going to find anorthosite. We'll show you some more information about that as we go along. So interesting, for sure, the contrast, the difference between these two spheres, the near side and what used to be incorrectly called the dark side, right? Because there is no dark side of the moon. Somebody wrote a song about the dark side of the moon? Okay, yeah. So he was wrong. He should have called the far side, but like the cartoon Far Side. So there's no dark side. Pardon? Came after Moonraker? Okay. And by the way, not only these basalt mare here, but you see one even on the far side. And we'll talk again, and this is very interesting. We'll talk more about that area right there. So let's talk about topography. So here's basically what we just looked at, near side, far side, and you can notice that the areas that are lower in elevation are in these blue, for the most part, the mare, because there was the impact there, and even though it's filled with basalt, it still is lower in elevation, if you will, than what we're calling the highlands over here. And even this, which we won't call it, is called the South Pole Aitken Basin. And that is much lower than the highlands. Now, what's interesting if you look at this topography, you start here at zero sea level, just like Earth, right? We have stuff below sea level and above sea level. But how do you measure sea level on the moon? There's no water. Anyone want to take a guess on how they figure out what the 0 point is? Yes. Average. The average. The mean radius. They have gone through and they have measured the mean radius of the moon is 1,737 kilometers, which is roughly 1,000 miles in terms of the radius. Because if you look, if it's 2,200 miles in terms of the diameter of the moon, then roughly 1,000 diameters is radius. So it's right. It's the mean radius. So they've established this as being the mean radius, and this is what's below mean radius, if you will, and this is above mean radius. And there's some significant elevation differences here. 7 kilometers, think of that. All you do is multiply by 0.6, and you get basically, what, 3 or 4 miles. You multiply 0.6 or 6 the kilometers by 0.6, you get 3,600. So there are some significant elevation differences here. Okay, now let's talk about the basalt. Here's the near side again, and here's where the basalt. Now this is primarily basalt, but if you really look at the basalt, 26% of the near side is volcanic basalt, and here is where that is in red. So it basically follows the areas that we talked about in terms of the mare. And on the other side, the far side, we have only 2% of the far side being basalt. So this little mare right here, which is unusual on the far side, is you can see it's dark right there. That's kind of a giveaway. It's filled with basalt. And if you look closely, even over here, and then compare it to the basalt image, it's got basalt. And down in here in the South Pole Basin, you have areas that have basalt. And the thought is that what happens is the reason why there's less basalt on the far side than the near side is because the crust of the far side is thicker than the crust in the near side. And so if the near side had very thin crust, so when asteroids hit, the asteroids penetrated the crust and basically released the basalt to actually come up and to flood those basins. Whereas here, most of this, almost all of this is much thicker, except down here, because we saw how low the elevation was there. So here, there were asteroid strikes for sure, but they weren't significant enough because the crust is too thick to basically to release the basalt from below the surface. So big differences between the near side. We'll talk later about why is the near side have a thinner crust than the far side being thicker. And somebody from, I think it's Pennsylvania State University, has a theory as to why that might be. It may be correct. So tidally locked, when we talked about dark side and far side, the moon is tidally locked to the Earth. That's why we only see one side of it. Okay? And what that means is when the moon rotates on its axis, that axial rotation is the same as the period of the moon going around the Earth. It's almost like if the Earth just faced the sun, and we were always facing the sun, it'd be really hot, wouldn't it? But anyway, if we went around the sun and we always faced the sun, our day would be the length of our year, because it would take a year for us to rotate once on our axis, and that would be the same year we would take the 365 days to orbit the sun. So tidally locked. But what's interesting is, even though it's tidally locked and we would see one side, we really see more than 50%. We really see 59% of the moon. Because the moon has some libration. Think it has a little bit of I call it a rocking motion. So we are able to see not just 50%, but 59% of the surface of the moon. They didn't know for the longest time what was on the other side of the moon. So as this cartoon says, I'll read it to you. Here's a space probe. Only a minute or so more, and man will have his first view of the other side of the moon. And it's hollow. Act 1, Scene 1. I guess it was a Star Wars prop after all, okay? And some people still say the moon's hollow. I don't know how they figured that, but anyway. So pretty cute cartoon. Anyone know the first year we actually had an image of the far side of the moon and knew that it was more than hollow, that it wasn't hollow, or it wasn't looking like this? 1959. It was a space probe. It was a Lunar 3 Soviet Union space probe, and it actually went to the other side of the moon in orbit, and it took a picture, not a very good picture, but it was the first picture. And then the U.S., in a Lunar Orbiter 5, I believe it was, went around the moon 1967 and took a decent photograph. And then the first time an astronaut looked, it was 1968, Apollo 8. I think the guy's name was Anders, the astronaut. He actually was in the spacecraft, the Apollo, that went around and looked down at the moon, and he saw the other side of the moon. And he made some comment about, it looks like my kid's sandbox. So I thought that was an appropriate way to use that cartoon. Now, before looking at this chart, how long does it take the moon to orbit the Earth? 28 days? But a month is 30 days, 31 days, depending on what month you're in, right? So this is, okay, there's several ways to look at this. So there's two kinds there's a sidereal and synodic. So what happens is, you can say that the moon rotates around the Earth once every 27.3 days. You can also say that it rotates around the Earth every 29.5 days. The difference is your perspective. If you look at the stars, far distant stars, okay, and you line up the Earth with distant stars, but when the moon goes around one time and you still see those same stars in the distance, that's going to be the sidereal being stars, sidereal day, which it does in 27.3 days. But if you look at this, in that month, the Earth has traveled around the sun, okay? Traveled 1/12 of the way around the sun. So in going around the sun, then if the moon started here, it's going around an orbit around the Earth. By the time the Earth has moved here, the moon has to go not just to this position, but it has to go further. It has to actually go to the position where it's a new moon. It's a new moon. Here it is here, where you're facing distant stars. But if you want to look at another new moon, where the moon is looking at the same face to the sun as it is over here, you have to wait 29.5 days. So that's the difference between a sidereal day or a sidereal lunar month and a synodic lunar month. So let it be on a test. So it's pretty straightforward. Just remember those two terms, synodic and sidereal. I like this chart because it's a lesson in Latin, okay? It's actually the name of the mare. And see if you folks know what these are. The mare, I can't even pronounce the Latin, tranquillitatis or something? That's tranquility, right? Okay, what about Chrysium? That's a tougher one. I had to look that one up. That's crises. Okay, Sea of Crises. And this one here is pretty easy. Serenity. And Nectaris is interesting. I don't know why it's nectar. I don't know why they named it nectar. Nubium. Anyone know what Nubium is? Mare Nubium. That's the Sea of Clouds. And Mare Humorum. That's not a funny mare. Humorum is moisture. Someone named that the Sea of Moisture. And then we have Imbrium, which is a sea of, what do you have all day today? Rain. It's a sea of rain. Did I miss any here? Yeah, this is, pardon? Fertility. That's the sea of fertility. Now, this one here isn't a mare, it's an oceanus, and it's Procellarum, and that's the ocean of storms. And the reason they don't call this a mare is it's much bigger than the rest of them. It's actually about 2,000 miles in diameter. So there was something that hit there at one time that would cause a 2,000-mile large impact area. Now, do you know the highest mountain on the moon? I mean, everyone knows the highest mountain on the Earth, Mount Everest, right? The highest mountain on Haleakala on Maui, 10,023 feet. We all know that, right? So what's the highest mountain on the moon? No one ever talks about the highest mountain on the moon. Okay. It's in the Apennine Mountains, And there are the Apennine Mountains. And this actually is Mare Imbrium, the sea of rain. And that mountain is Mount Huygens. Huygens. Remember the Huygens? We had the Cassini. Huygens was a part of the Cassini spacecraft that went down basically into Saturn. So that's Huygens, Mount Huygens. It's 18,000 feet high. And that went too fast. I think I had that on that chart. I actually remember 18,000 feet because we're going to talk about that in a minute because there's a little bit of an issue with it, or a question at least. Okay. There we go, a little circle. That's where Mount Huygens is. And in context of the moon, here is Mare Imbrium, the sea of rain, and that mountain range is right in there. The other side of the moon, strangely enough, has a lot of Russian names. We have von Karman. I don't know if von Karman was Russian because he actually came to this. He may have been Russian initially. He came to the U.S. and he was one of the leaders at Caltech at the Jet Propulsion Laboratory in the 1930s. That's von Karman. But Korolev is a relatively famous, at least for Russians, a famous rocket scientist from Russia. And Mendeleev, I believe is the same one that worked on some genetics in terms of biology. Any other ones up here that I don't recognize? Well, this one here, I can't pronounce it. It's not TSIO, Chikoskoy, whatever. Oh, Gagarin. Everyone know Gagarin, the first man to orbit the Earth? So anyway, the far side, the Russians apparently got there first in terms of orbiting the far side and got to name some of those. Although the Apollo is one name here, and a few of these, Moscow Sea, and you'll see some more as we go along. But that's Moscow Sea is this very dark mare that's filled with basalt. So this chart is a nice summary of everything we've done on the moon, beginning with the Russians, Soviet Union at the time. They sent about 15 different Lunar, these items that are like in an orange. These were Lunar landings, about 15 of them. I've only got a few on this chart. And those were sent to the moon between 1959 and 1976. So they did a lot of work with sending probes to the moon in that time period. And then the Surveyor, we came along and sent 7 to the moon. 5 successfully did a soft landing between 1966 and 1968. And the Surveyor landing spots are shown right here. 1, 2, 3, 4, 5, way down here. And of course, the Apollo, there were 6 Apollo missions, 1969 to 1972. And you can see the 1, 2, 3, 4, 5, 6. One thing that stands out, most of these, they were playing it safe. So most of these Apollo landings were in the mare because it's relatively flat, so it's not going to be an issue with being on uneven terrain. This was Apollo 16 down here, and they actually got some samples from not the mare, okay, not the basalt, but they got some samples from the highlands. So we can have that anorthosite we talked about, that feldspar that's in the part of the moon, 84% of the moon that's covered in anorthosite. And most recently, Chang, C-H-A-N-G, apostrophe E, they've sent several to the moon. Of note is Chang 5, which landed up here. I have a chart on it coming up, but it was significant because it actually, first time in 45 years, it returned about 4 pounds of lunar material from the moon. And it was interesting because what the Apollo astronauts picked up, they picked up rocks in 800 pounds, 841 pounds. And those samples have been dated, and they are between 3.5 and 4.5, 3 to 4.5 billion years old. Well, the rocks that the Russians picked up were a billion years younger. So they were at about 2 billion, not 3 to 5 billion. So that gives them some additional information that scientists didn't know about the age of some of the rocks on the moon. And here, it's been 50 years. Think they'll ever come back and clean up after themselves? And the other one's looking at a telescope saying they're busy not cleaning up after themselves at home. So I have to thank Safan, who's online here in Oregon. She's the one that mentioned that there's a cartoon she saw with these guys or gals, these guys or gals, picking up after or looking at the trash that the Earth people dropped off. And now I'm wondering, maybe these are moonrakers. I mean, they could, they could be those mystical, unknown moonrakers. Okay, this is Shang 5, and if anyone knows Chinese better than I do, they may have a better pronunciation than Shang 5. This is it landed at Mons Rumker, and that launched. They went there quick. They launched in 2020. They went there, they picked up the rocks, they came back, and they delivered it back, I guess, to Siberia in December. So they did it real quick on the moon, get some rocks, and bring it back. 4 pounds, 4.4 pounds or so. It kind of looks like our. Look at that. Look. I wonder where they got that idea. Let me go back one. Oops. Where have you seen that before? The copycats? Are they copycats? I thought. They have all kind of airplanes that look like our airplanes. Of course, the Russians do too. Okay. Anyway. So this is Shang 4, which is a couple years earlier, January of 2019. And it landed on the far side of the moon, the South Pole Aitken Basin. And it is basically their first landing on the far side of the moon, but it's the first. We haven't put anything on the far side of the moon yet. We're planning it to, but they kind of broke ground on that by being ahead of us by putting something on the far side. It hasn't not returned any, samples, but at least they put something, and I think it's actually have a rover there too. Now, how the moon was formed. This theory is not too old, maybe a few decades, but this is called the giant collision hypothesis. But the thought is that right after the Earth formed about 4.5 billion years ago, a very large object, roughly the size of Mars, and it's called Theia, Theia. The thought is this very large, planet, if you will, or protoplanet, smashed into the Earth, and what that did, it melted this protoplanet and a good part of the Earth, and then the debris from that created a ring of debris around the Earth. And that ring of debris, we had a ring, just like Saturn has a ring. We had a ring for a few, maybe million years, whatever time period it took for that material to coalesce into our moon. That's where they think the moon came from. And there's the other item that we'll talk about now is because the moon has a much smaller core than the Earth, there's a confusion is why is their core smaller? They have an iron core just like we do. Iron, sulfur, probably some nickel. But it's much smaller than scientists would think it should be. The thought being that the iron that was in his body here during this collision, a lot of it went to the Earth's core. And that's what what's left became part of the moon's core, which is much smaller than would be anticipated. Yes.
So is the mechanism unique to our Earth moon, or is it similar to how other moons and the other planets were formed?
That's a very good question. Okay, the question is the technique similar? Is that how other moons formed? We know for the longest time we thought just Saturn had rings. And then we went to Jupiter and we said, oh, hey, Jupiter's got rings too. Not as beautiful and extensive and majestic as Saturn, but there's some rings around Jupiter. And also rings around Uranus and rings around Neptune. They have even found recently, I read this in the last few months, they found a ring around an asteroid. So the whole ring concept is not unusual. That's a good question. I think the current theory, like let's take Saturn, don't think it was necessarily a collision because things will collide with Saturn or Jupiter. And since they're most of it, they have a deep in the depths of Saturn and Jupiter, there is a core, maybe as big as the Earth or larger, but there's a lot of gas. There's hydrogen, helium, and especially there's methane. So that wouldn't really cause an explosion per se that would cause this debris. So the thought is that if a planet or if a moon gets too close to a body, okay, there is a limit. It can only get so far, and it breaks up and becomes a ring of debris. So I forgot what that distance is. I think it's called the Chandrasekhar limit, and it's a certain distance. We have a Chandrasekhar limit. If our moon ever got close to us, it would basically dissipate, or it would break up into a lot of pieces and become like a ring. So I believe it's the Chandrasekhar limit. So I think that that's what happened with the rings around not only Jupiter, Saturn, but also the smaller, very small, almost ephemeral rings around Neptune and Uranus. Does that answer your question okay? I've never heard any talk about a collision theory creating the rings around anything but how Earth formed. Yes, question?
I'm pretty sure you don't know no radius.
Pardon?
No radius. Chandrasekhar's long enough.
Yeah, he's about 1.44 in terms of white dwarfs.
Yes.
Yeah, yeah. If the material drops onto and the mass of that white dwarf gets more than 1.44, then it goes supernova.
Right.
Okay.
I think it's no radius.
Who's?
No radius.
I'm not okay. That's probably so. Yeah, I forgot the names, but you're right. Chandrasekhar was the individual, very brilliant Indian, Asian Indian, that came to this country as a young man, and he's the one that came up with the Chandrasekhar limit in terms of why white dwarfs go supernova. Yeah. Okay. Thank you. Now this is very cartoonish, but once the moon started to coalesce from all this material, it was very hot, and initially, the heavier stuff goes towards the core, unmelted primitive material, and a magma ocean. And then, the next step is you start having light material, plagioclase. Plagioclase is feldspar. That's another word for feldspar. There's orgiclase, plagioclase. It's feldspar. It's what makes up what we talked about being that anorthosite. So that is lighter than olivine, pyroxene, and iron and nickel for sure. So the plagioclase, the feldspar, floats to the top and creates a crust, and then you have a mantle. So you still have that interior core. You have a mantle, the mantle being made up primarily of olivine and pyroxene, and olivine is fascinating. We'll have a couple more charts on olivine and pyroxene. These are usually items in the mantle. Even the mantle of the Earth has lots of olivine, pyroxene. And up here then, between the mantle and the crust, so something creeps in. It's called creep. It's called creep because the geochemists or the geologists or whatever you want to call them, they have a sense of humor. So creep is an acronym. The K stands for potassium because K is the symbol for potassium. REE is rare earth elements. When there's about 15, I believe it is, rare earth elements that are between 57 atomic number and I think 70, 75 or so. But anyways, about 15 rare earth elements. They're not that rare, but they're called rare earth elements, and a lot of them are mined, and they're not rare, but they're not really. They don't have any areas where they have heavy amounts of any one particular one, so they're kind of hard to mine. But the rare earth elements are the REE. The P, if this stands for potassium, the K, what's the P stand for? Phosphorus, right. So that's creep. Potassium, rare earth elements, and phosphorus. And it's thought that the creep is between the mantle and the crust, although there's some controversy about, well, they don't quite know how it formed there, and it's kind of, but basically it'll come to the surface, especially the next stage you start having impacts, and with the impacts they do several things. They bring up some of the mantle material to the surface. They also create some openings for that magma to come and to give us our basalt flows. So that's how we get to the evolution of the moon. Now, talking about olivine. Anyone recognize where this is in the Hawaiian Islands? Pardon? Big Island. And it is, you've heard of South Point, right? South Point, this is real close to South Point. It's a green sand beach. And it's kind of cool. If you want to go there, I've been there a couple times. It's a long walk. From the parking lot, it's like a 3-mile walk in, 3-mile walk back. Although last time I was there, some people were charging $20 for a ride in the truck. But who wants to do that? I mean, that's no fun. And there must have been, 25 people in a truck that should have only been holding 10 people. But they were making some money on it, right? But anyway, if you ever go here, it's fascinating. It doesn't look green at first. It looks kind of like regular sand, right? There's a handful of it. But if you take a hand lens to this, here's what you get. You get all these little, I want to call them crystals, but they're not really crystals. They're really called phenocrysts. They're little pieces, for the most part, the green are olivine, And you have a little bit of basalt in there, and some white stuff looks like for maybe feldspar or maybe quartz. But very interesting. There's only about 3 other places in the world. I think there's a beach in Norway. There's one, I think, in Guam, maybe the Philippines, that have green sand beaches. But it's in our volcanoes. It comes up from the mantle, and some places like this we're fortunate enough to see the olivine exposed. Okay, now a little bit of a view of the cross-section of the moon. So we have the mantle. Well, let's talk about the crust first. We have the crust over here. Roughly, it varies in thickness. I got a chart on it, roughly between 10 miles and 30 miles in diameter. In thickness. So that crust is made of silicate and oxygen. The silicate, most rocks have silicate. It's got magnesium, iron, primarily calcium and aluminum make up the crust, and i.e. that is the feldspar. The feldspar is the silicates plus calcium, sodium, aluminum, and that's the anorthosite we talked about that makes up most of, at 84% of the surface of the moon that's made of that crust. There's also some minor things, titanium, uranium, thorium, and potassium. Here it is average 30 miles thick. The mantle has the olivine and pyroxene. So these items are in the mantle area, and they show up on the moon, but only sporadically where there's been access to basically below the crust. And you can see the chemical symbols here. Olivine, Si4, one atom of silicon, 4 of oxygen, and magnesium or iron. And there's really 4 types of olivine, depending upon whether it's mostly magnesium, mostly iron, or something in between. There's actually 4 different types of olivine. And the pyroxene has the same silicate and oxygen, magnesium and iron, but also calcium, magnesium, and the difference being it's in the S2O6, but also, for example, this one down here is calcium. So those are the primary constituents of the mantle. I've got a better chart here, but you have an inner core, solid core, just like the Earth. Now this is all theory. Basically, there's been lunar quakes. We left some seismographs on the moon, so whenever there's a little bit of movement, a lot of it is if it's hit by a decent-sized asteroid or a meteor, then it'll show up in a seismograph, and it'll send some seismic waves, and we can measure those. But you have a solid inner core, a fluid outer core, a partial melt, and then the mantle. And then the next chart is showing a little bit more detail. Here's that anorthosite crust, and the mantle again. You have the upper mantle, middle mantle, and then the core, the solid and the outer core, and the partial melt. What they think is the partial melt. And again, primarily iron, nickel, minor amounts of sulfur and iron, or sulfur and nickel. The interesting, what they've done. The moon is one of the few, between the moon and Mars and the Earth, we know more about those 3 bodies than anything else in the solar system. So this is a lunar geologic timescale, or also known as a selenological timescale. And by the way, I was going to mention earlier, I really think it's not fair to call the moon, because you don't have a dog or cat and call him dog and cat, right? You go home and say, hi dog, how you doing? Well, the moon is so generic, and we have so many of them in the solar system, everybody's got moons. So why are we calling it the moon? Shouldn't we call it, I think Selene is cool. That is the Greek goddess of the moon. So I'm think we ought to change the name of the moon. Good luck on that one. But the ages of the moon, the most recent age is called the Copernican, because there's a large crater called Copernicus. And when you get older, there's the Eratosthenian. I can never pronounce that. Anyone want to make it better try at that. And that's a long age that goes from about 3.2 billion to about 1.1 billion. And then prior to that is the Imbrian, and prior to that, very, very small n here, a Nectarian and a pre-Nectarian, going back 4.5 billion years. Because if the Earth's 4.5, the moon's about the same age, 4.5 billion years. So these are established, though, not based upon, like on the Earth, there's some geological events. We have the end of the dinosaurs, and that ended the Mesozoic. We went to the Cenozoic and the Cretaceous and all that. So we have events that kind of mark our geologic ages. We don't have that in the moon. What they do, they look at large impact events and how they would affect the surface of the moon in terms of the formation, or changes in crater formation. If they can tell ages, because if one crater comes on top of another crater, they call it superposition, then you know the crater that is basically, I shouldn't say basically all the time, but the crater that is impinging and wiping out a previous crater, that's a younger crater. The older craters are the ones that, and there's some erosion because you do get some solar, you get a lot of meteor impact over billions of years. So you do have some, not erosion like you have on Earth, but there is some degradation to the craters. So looking at the changes in crater formation, large impact events, and that size frequency distribution, they came up with this very rough scale. Now they admit, though, they have so few lunar rocks. You know, we picked up, I think it was 841 pounds in the Apollo program, and we can date those, but it's very difficult to then date those and try to put those in the context of, are they pre-Nectarian, are they Imbrium, are they Copernican? So they have a difficult time, but this is their early, come back in 100 years, and this may be really fleshed out, okay, in terms of the ages of the moon. To compare it, here's the Earth. We got lots of detail. And of course, we're most familiar here with the Paleozoic, Mesozoic, and Cenozoic, and less so farther out here. In Mars is tough too because not a heck of a lot happened. A lot happened to the Earth geologically because of plate tectonics. I mean, our ocean basins are no more than 200 million years old because of plate tectonics. So there's a lot going on the Earth because of plate tectonics. That doesn't happen on Mars, doesn't happen on the moon. So even Mars, though, they have the Hesperian, the Amazonian, and they have not only a crater density. So this is based on crater density. If you have an area that only has a few craters, well, then you know there was probably some volcanic activity and it wasn't very old. Whereas if you have a lot of craters, then that's going to be an older terrain. They have a mineralogical scale, which I haven't looked at very closely, and I can hardly read this one here. So looking at the mineralogy that we know about on Mars, because we do have some meteorites or meteors that fell, became, you know, the meteors when they come through the atmosphere, they're meteorites once they hit the ground from Mars, as well as the moon. We have some meteorites from the moon also, which help us to understand the content of what minerals, what rocks are on Mars and the moon. But I just wanted to show the comparison. And a simple crater, kind of how it forms, you have this impact ejecta, so you have, when it hits, there's a lot of stuff thrown out here, and a lot of fractures, you have a lot of impact melt because of a lot of the pressure of that asteroid or that meteor, fractured bedrock down here, and you have quite a bit of breccia, which is basically pieces and parts. It's like a conglomerate, but they're all rough pieces and parts that are cemented together. That occurs a lot in these craters. And then that's a simple crater. A more complex crater is where you have a center mountain. And that's a rebound. It's like an isotopic. It rebounds. The pressure is so great and it bounces back up. And it's a rebound. It's kind of like glaciers do the same thing. Glaciers actually suppress the land. And when the glacier melts, the glaciers melted what? 15,000 years ago, 12,000 years ago, and Great Lakes, the land around the Great Lakes are still rising because of that rebound, thousands of years later. So there are some interesting center peaks. Here's another image, and by the way, this has a center uplift here with these isostatic was the word I was looking for, isostatic rebound, and you have these terraces created with these faults because of the pressure. This actually is a center mountain in the crater Tycho. I'm sure you've heard of Tycho. Tycho is very prominent, got a lot of rays going out, and this is almost, I think it's a little over a mile high. So that is one significant rebound after that item hit and created Tycho crater. And what happens with these craters, they are really a window into Mars. Because with spectroscopy, we can tell the materials that are in that crater. We can tell what's on the outside, but this gives us insight what's below, in some cases actually in the mantle. So spectroscopy gives us that information. concentric rings that we find around a lot of craters, they have a lot of olivine that's been dredged up from the mantle. Late heavy bombardment, this is an event that occurred throughout the whole solar system, somewhere between 4.2 and 3.9 billion years ago. And that late heavy bombardment created many craters on the moon. Probably a lot on the Earth, but many on the Earth have been removed by plate tectonics. The oceans cover 71% of the Earth, so as well as erosion. So we don't have much information about the number of craters that at one time hit the Earth. And thin crust, especially the areas that are only 10 miles, the crust, they're much easier to expose the material if that asteroid hits a thin crust area versus a thick crust area. And here are the silicate minerals. Again, olivine and pyroxene in the mantle. Plagioclase, i.e. feldspar, i.e. anorthosite, is in the crust. And Lunar Reconnaissance Orbiter. This has been a fantastic craft. It arrived in 2009, still going strong. They hope it's going to be there to 2026. It's done a lot of these really detailed images of the moon. So it's done, it ought to get a Nobel Prize if you give a Nobel Prize to a spacecraft. Same thing around Mars. We have the Mars Reconnaissance Orbiter, which has given us some fantastic resolution pictures of the surface of Mars. And if we have time, at the very end, I've got a little bit of a video on some of those pictures from the Reconnaissance Orbiter. Okay, so here we've gone about 45 minutes, so break time. And if you can't read that, oh, it's gone. I need to go back to that. 2049, space probe lands on Pluto. Anyway. So let's take 5, and we're kind of on time I'm halfway through. And again, feel free if you guys want to take off. I'm not counting the number of people, so.
I just want to get off that hard chair.
Everybody needs to sit in a different place, so I won't know who left. See, it went 50 minutes, but it seems to me like it was like 20 minutes.
You know your material too well.
Getting a little bit of a mic bump.
Mike. because they haven't recovered yet from pandemic, but
So yeah, basically you would check for Haleakala amateur astronomers. Send me an email and I'll put you in touch with them.
or whoever it was.
Who was it?
Okay.
Yeah. And in what, or are you thinking of Maui Astronomy Club?
No, that one's gone.
Yeah.
Gone.
Yeah, Becky moved to the
Yeah, I used to
East
do
Coast.
that.
Right. There is the Haleakala Amateur Astronomers still, and I can put you in touch with them.
Oh, great.
Okay. Ready?
All right. Yes.
Okay. Couple things. Talking to JD, the Roche limit is what happens is, and for the Earth, if our moon, I don't know how they quite calculate these, if our moon got within about 11,000 miles of the surface of the Earth, then what happens is the tidal effect of being so close to the Earth would overcome the gravitational pull that holds the gravity holds the moon together, and it would basically break up and become a ring. Okay, the Roche limit, and so each planet would have a Roche limit. It'd be depending upon the size of the planet. The other thing, I don't know if I was clear in terms of somebody asked about, I think they wanted to know how various moons form, because it's, well, like as JD mentioned, some of the moons, there's so many of them, not 92 around Jupiter, a lot of those could be captured asteroids, because there's so much going on in the solar system. There's asteroids, there's comets that it seems kind of quiet out there on a human lifetime, but over many, many millions of years, lots happening. So things get captured. There's a lot of collisions. Uranus rotates on its side. So, it doesn't rotate like we all do with the pole sticking up, although we're different angles. We're 23 degrees, and Mercury's pretty straight. But Uranus actually doesn't revolve on an axis going around. It actually rolls on its axis going around the sun. So how does that happen? They think the answer a lot of times comes down to collision. At some point in its history, something hit it. And the other one, I believe it's Neptune, goes the right direction. It's not retrograde, but I think it's a Triton. I think Triton goes, the moon's going this way. We go around, our moon goes around the Earth the same way we rotate on an axis. But if I'm correct, remember correct, Triton around Neptune, it goes the opposite direction. It's a retrograde orbit. So the moon, or Neptune's going one way, and the moon's going the other direction. How that happens, because we think that a lot of moons some moons formed in place with the planet. You have this proto-nebula, and gravity takes over, and it coalesces, and there's a rotation, and there's going to be a little bit of material that didn't make it into that where the planet is. It forms a moon, and they all kind of have that same angular momentum, but that doesn't always happen, either because it was captured or there was a collision. And they don't know, to a large degree, how a lot of these, they have theories of how they happened, and they can look at something and say, well, that's weird, so someone has a theory as to how that may have happened. Yeah. So does that help a little bit?
Yeah.
Okay. So let's get away from Pluto here. So I just want to show this, not spend a lot of time, but there are some very detailed lunar maps. And as you can see here in this one, it actually shows up brighter in my computer than it does in the screen. That's kind of weird. This is darker blue. But what they've done is they've tried to label these in terms of the geologic or the lunar scale. Here's a nectarian, which are the oldest ones, nectarian. So this is a brown nectarian would be over. These look like a lot of nectarian here. And then it goes to Imbrium, and then it goes to the Eratosthenean, and Copernican being the youngest ones. There's a lot of detail. I just want to show the concept. Now, the other thing to point out is, look at this. They had to give the moon latitude and longitude. Otherwise, how are you going to know where you are? And I actually had a chart showing that, but I can talk about that. Here's a great chart of Copernicus by itself. Copernicus is 56 miles in diameter, about 2.5 miles deep, and the center peak here, the biggest one, there's several of them, over 4,000 feet. And the problem I'm having with these charts, they're not, there's no consistency in terms of the colors they use to describe these ages. So, except the only consistency may have occurred recently, because there's a chart coming up in a minute, I'll show it to you, that is finally the U.S. Geologic Survey came out with this very detailed map which, of the moon, which I think could even be used when we eventually go back to the moon. This is Copernicus with a little bit of a view, of a rotation. You can see the crater. And that caption will go away any second now. There we go. But again, I don't have the caption to describe what this is. Here's just the center peak. That's a certain color. You know, some of this could be erosion, where you have the cliffs here kind of slough away, which we've seen that a lot on Mars. Yes? For the most part, this is actually made by the European Union. Project received funding from the European Union. But they have access to LRO. So they probably use that same. We share information with the European Space Agency. I mean, that is a pretty good detailed map, really, yeah. And let's talk about the largest crater on the moon. So this is the South Pole Aitken Terrane. It's also called the South Pole Aitken Basin. It's also called SPAT, right? And you can see, and this is highlighted because this is darker than maybe it would be if you looked at it, and this is lighter. So this dark area here is the basin, which is considered to be the largest crater in the solar system. You know, I looked at that. It's 1,600 miles in diameter. It's kind of, I thought maybe there's a Caloris Basin on Mercury, which I think I gave a talk on Mercury a couple of years ago, which is like 600, about 1,000 miles in diameter. But this is actually wider. However, if you look at the other side of the moon, remember that Oceanus Procellarum? That's supposedly 2,000 miles in diameter. If that was created by a crater, if that basin, that Mare, was created by an asteroid, and it's considered a crater, then that would be bigger than this. But I don't want to argue and take the nomenclature of this being the biggest crater in the solar system. And the deepest is 8 miles deep. But it's quite unique. Here is the lunar South Pole, where the arrow is. Unfortunately, there's no pole there. But on this map, it's a pretty good view. And again, these type of photographs would be from the Lunar Reconnaissance Orbiter. They have identified 11 potential lunar landing sites for Artemis 3. You remember Artemis 1 got some publicity. Artemis 1, this large rocket that was sent, it's a precursor to what's going to take people back to the moon. They launched it, and it went not only around the moon, but it went quite a ways beyond the moon, okay? And Artemis 2 is supposed to launch in 24, and I think Artemis 2 may have a crew on it that does a circumnavigation and goes around the moon. But Artemis 3, which you're looking at 2025, don't hold your breath, or don't put any money on that, because things usually take longer than we anticipate. But they plan right now for Artemis 3 to land on the South Pole area of the moon. And they've actually identified 13 potential landing locations. I mean, they want the landing locations, because the reason being, they think that that's a real cool place, because there could be literally cool, really cool in the shade of the craters, but very hot not in the shade. Oh, there's water in the shadowed areas that never see sunlight. So they think that's a source of water. Water is important, because it doesn't take much to break water, H2O, down into hydrogen, fuel, oxygen to breathe, and water to drink. So there's 13 sites they're looking at and analyzing when they actually land on Artemis, with Artemis 3 sometime later in this decade. The nearest thing that's coming up is this VIPER. They must have a hard time coming up with these acronyms. Volatilis Investigating Polar Exploration Rover. And this was supposed to launch in 2024. I got a short video. Tell us a little bit about it.
Decades of study that the moon has water, but where and how much? We know from decades of study that the moon has water.
Can you hear it okay?
But where and how much? In 2023, a robotic rover will explore the moon's surface in search of water ice. NASA's VIPER moon rover will perform the first resource mapping mission on another world, using advanced instruments and tools to determine the location and concentration of water on the moon.
To send VIPER to the moon, we're leveraging industry as part of our commercial lunar payload services program. A program designed to send science instruments and technology payloads to the surface of the moon. VIPER represents a very different development paradigm. We are developing each instrument to launch an eclipse ahead of Lunar, totally flipping on its head how Lunar is truly creative. An industry partner will launch Viper to the South Pole, a place where no human or rover has
The
ever
rover's
been
survey
before.
will provide
The
scientists with the
rover's
most
survey will
detailed
provide
view of the
scientists
moon's
with the
water
most
to
detailed view of the moon's water
to spots
date,
where water
and
could
to
be
spots
harvested
where
by
water
future
could be
astronauts.
harvested by future astronauts.
Viper will be the first resource mapping mission on the surface of another celestial body. It represents a new kind of mission for NASA in which the objectives of advancing science and human exploration are closer than ever. The measurements that Viper's instruments will make can help us understand the source and distribution of the water and other volatiles on the moon, giving us insight into the evolution of the moon and the Earth-Moon system. The moon's water is also a precious resource that could be extracted to support human exploration of the moon and beyond. What we learn from Viper will bring us a step closer to developing a sustainable, long-term human presence on the moon.
I think. Is that better? Yeah, that's too fast. Oh, oh my gosh. Wow, thanks. Where'd JD go? We okay, JD? Oh, okay. Okay, so
We know from decades of study.
so let's look. We talked about. I mentioned the 1,600-mile diameter of the South Pole Aitken Basin, depth of about 8 miles. Fascinating, because topography is such that this is quite deep, and they really feel strongly that there was some kind of a collision, some kind of a large asteroid that collided over 4 billion years ago. And there's the South Pole in comparison is right about there. So it's not quite on the pole, but it's a little bit off. And 500 kilometers. So they say, I've seen different numbers, they say there's a big island, and the big island is 150 kilometers. The widest distance is 150 kilometers. So I tried to make this last night, make this small, so it'd be 150 kilometers, but then you wouldn't even be able to see it. And they make, I guess someone made a good estimate that there's a metallic, like a large mass of iron that's buried here, and they estimate that it's 5 times the size of the island of Hawaii. So I've also have one chart saying it's the size of Denmark. So I'm not too sure how we compare the size of Denmark with 5 times the size of Hawaii, but someone liked Denmark as a comparison. And here another little view of it, likely made of nickel iron right here. Here's the core. Extends to a depth, I think, of 180 miles. And here's what spans 220,000 square miles, larger than Denmark. Anyway, left by an asteroid maybe 4 billion years ago. Lump of metal in the moon. This is a nice cartoon. It's oversimplified, but it kind of gives you an idea. And there are 3 types of terrain. There's what's called the procellarum creep terrain. Remember, procellarum was that sea, the oceanus procellarum. And creep, we know what that is now, potassium, rare earth, elements, phosphorus, terrain. That is where the basalt, that's the thinner areas where the basalt has actually, this is the thinner part of the crust, and when it was hit by asteroids, large asteroids in past millions, billions of years, it created those mare, and creep is that material that's between the crust and the mantle, which has now been exposed, and there's these mare basalts. Over here, and some down here is the FHT, which is feldspathic highlands terrain. Read feldspar highlands terrain. Read that anorthosite, okay? So that's the anorthosite, which is a much thicker crust. And then spat. Spat is considered that third terrain. However, they also say that, well, is spat really a third terrain, or is it just this large object that hit into the highlands terrain and created this unusual large crater? Maybe there's only 2 terrains. the reason the theory that's come up recently with the Pennsylvania State University, why is the far side of the moon thick crust, and the near side thin with all the basalt? Well, the thought is that once that Theotite, that Mars-sized planet or whatever it was, hit the Earth 4.5 billion years ago. Oh, we have a slam dunk.
Yes, you're going to comment on YouTube. I thought we would. Yes.
Slam dunk. Is that good?
Yes, I think that is good.
Oh, okay. Slam dunk. So there's a slam dunk right here when the spat hit the. No. So the theory they came up with is when that Mars-sized object hit the Earth, through all this material, the Earth was really hot. I mean, this was the pressure. You know, the Earth was like thousands of degrees. And when that moon formed from that ring, and when it became a solidified object after a few millions of years, the heat from the Earth was basically caused this area, the near side, not to coalesce into a crust as readily or as thick as the far side. The far side didn't have that heat from the Earth that was thousands of degrees. I mean, 7,000 degrees, the surface of the sun is 10,000 Fahrenheit, 6,000 centigrade. So you're talking about something that may have been as hot as the sun, not too far away, and that heat prevented this from forming a nice solid crust as soon as the far side could. That's the only theory I've ever seen, and it's a recent theory that came up as to why this is a thin crust and this is a thicker crust. Okay, GRAIL. This is fascinating. GRAIL stands for Gravity Recovery and Interior Laboratory. So in 2012, it was sent up. It only operated for a year. That was all that was needed. There's these two washing machine size satellites that were in orbit around the moon, and they were called GRAIL A and GRAIL B. But they did a little bit of a contest, and they contacted, I think, several hundred elementary schools throughout the country to name these besides A and B. And there was a school in Bozeman, Montana. They came up with the name Ebb and Flow. So instead of being GRAIL A and GRAIL B, they're Ebb and Flow. And the idea is they were in orbit around the moon, and they were constantly, of course, talking to each other, or figuratively talking to each other, and the Earth. And as they went around the moon, as the gravity, you know, as one was, they were between 40 miles apart and 140 miles apart, and the distance would change. So if the one that was in front, if it hit an area which had more gravity, it would accelerate, and it changes between the distance. And it was so accurate, incredible, the accuracy. They could measure the distance between ebb and flow 1 micrometer, 1/1,000,000th of a meter. 1 micron. That is a pretty small distance change, only 1/1,000,000th of a meter. Oh my gosh. So with that kind of a resolution of the distance between these two, they did a really nice job coming up with a map of the gravity of the moon. And the red is where the gravity is heavier, or should I say stronger, and the blue is where it's weaker. So how do you explain that? Blue is weaker. Apparently there was a crater, so you have less material there. Heavier here, yeah, maybe there's a crater, but maybe there's something buried there, some large metallic object, some large iron mass. And this is a kind of a Mercator projection showing it as a rectangle. And you can see here's the South Pole Basin right here. I just think it's cool that they got the resolution. Look at the detail in that resolution. And there's not, this is also fascinating. A gal. Anyone know what the measurement of a gal is? G-A-L? A gal stands for Galileo. It's a measurement of gravity. It's a measurement of the acceleration because of gravity. So you may remember high school physics. If you drop something without thinking about the atmosphere and that holds it back, but if you drop something, it accelerates 9.8 meters per second squared. And then I think in this country we used to say 32 or 33 feet per second squared. But 9 meters per square. So looking at this, a gal, G-A-L, by itself is an acceleration of 1 centimeter per second squared. Pretty small. Yes, question?
So down there in the South Pole, where supposedly that big heavy object is buried underneath,
Yes.
why is the gravity so light
Okay, my answer to that would be there may be a large object buried, but that large object is going to increase the gravity. You're right, but I think it's a net effect, and the depth of the hole is big enough that it compensates for that heavier object. Well, 8 miles. I think I said 8 miles. So it's kind of a. You're right. By itself, the mass would cause more gravity. A hole without a mass would cause less gravity. Put them together, and it's a net effect, which is going to be more powerful. So 1 gal is 1 centimeter per second squared. So if you look at 9.8 meters per second squared for the gravity on the Earth, we are 980 gal. We're 980. And looking at this, the moon, by the way, the moon, you remember this, the moon they always talked about, that 1/6 the gravity of the Earth, 16% the gravity of the Earth. So the the gal on the moon is going to be not 980 GAL like the Earth, but it's going to be 160 GAL, okay? So what this measures, this is weird. This is a 0 point, which means this is the average. Instead of showing you absolute numbers, this chart shows you averages. So the average of the moon entirely is right here in this yellow, and then the red is an increased amount of gravity, and the blue is less gravity. So that's how you look at that chart. So that's the 1,000, this is mgal, which is milligals, which is 1,000th of gal. So 1,000th of a gal times 1,000 means this number right here on the scale is a gal, GAL. So it's a way to measure gravity. But it's a very subtle difference if you look at the fact that this is just looking at a very small variations in the gravity. And we talked about crustal thickness, but this shows you the thickness again. And if you look at the near side, these little stars show where there's olivine-rich exposures. And this is where the basalts and the marais, the materials in the mantle have come up, and they show a lot of olivine exposures. Fewer on the far side, which you'd expect because it's a thicker crust, and the olivine forms in the mantle. You notice this I think was the Moscow Sea right here, as I recall. There's a lot of indication. We know there's olivine here because, again, it is a mare is filled with basalt, so it went down into the crust. There was such a significant item that hit. And around the South Pole Basin, too, there's some olivine. And I show this because the next one will show you the topography again. So I wanted to compare. There's a strong correlation between this chart with crustal thickness, and the thicknesses being less in blue, more in red, and this being the far side, thicker crust, and except for the South Pole Basin, and this being the near side, thinner. And if you look at these two back and forth, you can see there's a very close correlation between topography and crustal thickness. And I thought this was good. These two scientists, of course these are false colors. The reds are really greens. The greens are reds, the blues are oranges, and the oranges are blues. Makes sense. Because everything is in false color anymore. This is one of the maps that I talked about, the USGS Geological Survey put together, and very recent, and it's probably the best map they've ever made of the moon, and I hope they standardize around the coloring here. So there's actually a little video, it's kind of cool, in rotation. This is called the Oriental Basin. There's a crater there, but it's actually a basin that's quite as significant. We can't see it. I don't think we can see it very well from the Earth. It's kind of on the limb of the moon. And if I go to the next chart, you can actually see, again, near side, far side, and the red, it's where for the most part, where the basalt is, and of course on the far side, you really can't see the South Pole Basin very well here. And I like this map because it really shows you the detail, although you get some distortion because it's that Mercator projection again, trying to put a round object into a rectangle. So I only show this just to show you, for that map, this is the kind of detail available. These are the map symbols. And again, it all follows that same, the colors are different than we saw, but it's that Nectarian, pre-Nectarian, Imbrium, Copernicus. So they're marking all these by the ages as best we understand them, but stay tuned, come back in 50 years and it's going to be probably changes to this, or further refinements. And then let's talk about some of the samples. This is olivine. Here's some of those green crystals. This is the first, one of the first lunar samples in 45 years. This is brought back by the Chinese. This is pretty small too. This is 1 millimeter right here. So that's a pretty small piece of olivine. And Apollo, we brought back 840 pounds. And this is some basalt. Kind of looks like some of the vesicular. This is where the gas escape causing these vesicles. And this is not too big either. This is, I believe this is a 1 centimeter cube. Apollo 15, and it was aged at 3.5 billion years. One thing interesting about the Apollo, those 800 pounds, they took a bunch of them in Houston back in the late 60s, early 70s, and they said, let's take some of these samples and put them in cold storage, i.e., I think this is actually in nitrogen. We're going to put them away, and we'll open them up in 50 years when we have better technology to study those samples. So the University of Arizona, one of their researchers, a young assistant professor, actually has access and will be opening some of those samples. And she has brought some back to the University of Arizona, Tucson, and she'll be doing some analysis with instrumentation that we didn't have 50 years ago. Now, you wonder if they're going to keep some of them for another 50 years. I didn't hear about that. But it'll be interesting to see the results that she comes up with. And not only her, but I'm sure there's other researchers around the world that were given access also. And this is, again, we talked about breccia, which is basically a conglomeration of pieces and parts and cemented with some lunar soil. Apollo 17, 4.5 billion years ago. And a lot of this is, there was so much over the years, there's so much stuff that hit the moon in terms of meteors and micrometeorites, and a lot of it was I don't want to say eroded, but a lot of the stuff became part of the regolith of the moon. So it's a lot different than it was, say, 4 billion years ago. And that's why this is so old. This is a lot of the pieces and parts in the lunar regolith that was put together in this rock. Great example of anorthosite, calcium and aluminum. You can see the silicon and oxygen, like silicates, but unlike olivine, which has iron and nickel, the anorthosites have calcium and aluminum. So that's a big difference. And brought back by Apollo 16. This is the one I said that Apollo 16 was the only one of those 6 Apollo missions that went into the highlands, not the basalt of the mare, but the highlands, where they picked up this great example of anorthosite, 4.2 billion years old. And another piece of basalt, 5 inches from Hadley Rill, 3.3 billion years old. Again, very similar to what we find in Hawaii, that basalt, very, very similar. And a lunar meteorite. This one actually, NWA 11444, what that means is there's a lot of these are found in the desert. And NWA means Northwest Africa. And the number of that meteorite is 11444. And again, over the years, things hit the moon and throw things up. They leave the moon because the escape velocity is not that great. And they go into orbit around the Earth millions of years, thousands of years later. We have about a little bit fewer than, almost 400 different known meteorites from the moon for a total of about a little over 400 pounds. And they tell us a lot of information about the moon. I love this chart. It looks a little bit crazy, but this is a great chart to understand igneous rocks. And how this works, you have volcanic rocks. Volcanic rocks are ones that come up to the surface and are spewed out of volcanoes. Basalt, for example, in Hawaii. Now, basalt isn't very explosive. It's called effusive. It comes out and it runs down the mountain, and we have some fire, volcanic fire fountains in Kauai. And these over here, between rhyolite and andesite, they're also volcanic, but they're very explosive, and I'll tell you why in a minute. So these are plutonic. Granite, plutonic meaning Pluto, the underworld, these formed underneath They did not come to the surface. So when these came to the surface, they cooled very quickly. The crystals are very small, whereas these that were below the surface cooled very slowly. That's why granite has the granularity. You have feldspar, you have basalt, you have quartz. So granite, granodiorite, diorite, these are all plutonic rocks. And basalt is the same as gabbro, except basalt is not crystallized. You need a really very powerful magnifying glass to see the crystals, where this rock here is going to have larger crystallization because it formed slower under the earth. And the way it works is it's all based upon the silica oxide, the silica. And if it has not too much silica, like basalt, 45, 50%, then it is much more effusive. It isn't explosive. But if there's a lot of silica up here in the 40, 55 to 70% silica, that like andesite, rhyolite, it becomes explosive because the silica prevents it. It prevents that magma from expelling its gas. Because the reason it's explosive when a volcano is explosive, it's got water, it's got gas, and they're trapped, and it becomes explosive when the magma hits the surface. So it's based upon the amount of silica that's in the item. What we have is, I think I have a show a little bit closer. So
does the silica make it stickier?
it does make it stickier, and it bonds. It actually bonds with the material, so it makes it tougher for that item to easily give up the gas. Yeah. Whereas the basalt could have the same amount of gas in it, but it doesn't have that stickiness. And the viscosity, and I got a chart showing viscosity. This is less viscous. It flows very quickly, whereas over here it's much more viscous. At these levels here, like to make granite or rhyolite, depending on, it's the same thing except this is plutonic, this is volcanic. You have a lot of orthoclase, which is a feldspar, and you have some quartz, you have some plagioclase, another feldspar, and down here muscovite. As you go over here to, let's say even granodiorite, dacite, you have very little orthoclase feldspar, you have more quartz, lots of plagioclase feldspar. When you get over this area, basalt, you have a little bit of plagioclase, but you got a lot of pyroxene and olivine. And over here, peridotite, which basically it's a rock that is, for the most part, made up of olivine, and it has pyroxene and olivine. So these are the items, even on the moon, which are in the mantle, and even on Earth they're in the mantle. And the chemical composition we've talked about, magnesium and iron with silicate. This, I think that actually goes over. There we go, to pyroxene. This has a number of different elements, plus silica and aluminum and oxygen. And then on the other side, we have, for the plagioclase feldspar, we have sodium, aluminum, calcium, aluminum, and then silica and oxygen. So those are some of the differences. More iron and magnesium here in these igneous rocks, and you have less over here because you have sodium, calcium. So the next one, these rocks over here are less viscous because of the less silica. More viscous over here, i.e. thicker, and they hold in that gas and they make it more explosive. These are hotter. Basalt runs much hotter than, say, rhyolite. And you have lower levels of magnesium and iron in the rhyolites and granites. You have higher levels over here in the basalts and the peridotite. So we're getting close to the end, too. Okay, some books, if you're interested. This is one that was called The Book of the Moon, in 2019, not too old. Number of pages, 103 reviews, 5.5 or 4.5 out of 5 in Amazon rating, and there's the price, hardcover or Kindle. And it's a cool book too. It's a little bit older, but it's got some great photographs in color. Moons, in color. I say false color. The moon's not in color. The moon's largest craters and basins, 5.5 out of 5, but only the author reviewed it. So what else is he going to do, right? And the geologic history of the moon. There's not a lot on the internet about the geologic history of the moon. So this is 2014. 3.9 out of 5, not too bad, 15 or 12 reviews. So those are suggested readings, and I thought I would share this with you. I'll do my best to read this. Called Moonlight. As a pale phantom with a lamp ascends some ruins haunted stair, so glides the moon along the damp, mysterious chambers of the air, now hidden in cloud and now revealed, as if this phantom, full of pain, were by the crumbling walls concealed, and at the windows seen again. Until at last, serene and proud, in all the splendor of her light, she walks the terraces of cloud, supreme as Empress of the Night. So my question to you is, who wrote that? Going once, going twice? Okay. Henry Wadsworth Longfellow. So if you want to, I've got a little 4-minute video that's kind of cool. I'll play this. It's from the Lunar Reconnaissance Orbiter, and it kind of highlights some of the things we talked about.
To nearly everyone, the moon appears to be a sterile, gray, unchanging world. But while the moon has remained largely unchanged during our own understanding has evolved dramatically.
Thanks to new observations, we now have not only unprecedented views of its surface, but a whole new tour of the moon that shows how both it and other rocky planets in our solar system have been shaped over billions of years. We'll start with one of the largest impacts, Oriental Basin, a feature that's as wide as the distance from New York City to Cincinnati. Using new elevation measurements, we can see the effects of what is likely the last giant impact event in lunar history, with its outer mountain range rising many kilometers above the lowest points inside the crater. The interiors of some craters in the moon's polar regions, like Shackleton, haven't seen sunlight in over 2 billion years. However, new measurements have created our best yet maps of these types of craters.
Interesting question.
Some impacts are invisible for other reasons. Although the ancient South Slope Aitken Basin is difficult to see from orbit because it is so large, new LRO topography maps reveal the largest impact basin in the Earth-Moon system, measuring several kilometers in depth and around 2,500 kilometers in diameter. Only the Hellas Basin on Mars rivals it in size. One of the youngest large-scale impacts on the Moon is the Tycho crater. This fresh crater may have formed only 108 million years ago, when dinosaurs roamed the Earth. We now also have an extreme close-up view of the crater's central peak, revealing a mountain with sharp edges, building-sized rocks, and a central boulder about the size of a baseball stadium. The Aristarchus Plateau is another recent lunar formation that has long interested scientists and astronomers. The crater itself formed in the same era as the Tycho crater, and what appear to be snaking river valleys were actually carved by ancient lava flows. Next, we arrive at Mare Serenitatis on the near side of the Moon. In December of 1972, the crew of Apollo 17 landed in the Taurus Latro Valley, marking the last time humans have visited the surface of the Moon. With images from LRO's narrow-angle camera, we can clearly see the evidence of that visit. In this image, you can easily see the base of the lunar lander along with the lunar rover, parked far from the blast-off zone. You can also clearly see the astronaut trails and the wheel tracks left on the lunar surface. We now head to the far side of the Moon, which cannot be seen from Earth. Our first stop is the Compton-Belkovich region, which shows evidence for young volcanic activity in the far side highlands. This feature is unique not only because it is isolated from other volcanoes in the area, but also because it is located nowhere near the Maria, where volcanoes are usually found. Also, on the far side, we find the Jackson crater, which, like the Tycho crater on the near side, has an extensive and complex ray system. In fact, this crater is often considered to be like a twin to Tycho. Finally, the Tsiolkovsky crater stands out as an excellent example of a far side crater filled with a sea of ancient lava, known as a mare. It is particularly interesting to scientists and other observers because of its isolation from other similar craters as well as its beautiful central peak. As we continue to study the Moon, our understanding of it improves, giving us new insights not only into how it has evolved over time, but also how other rocky planets in our solar system have come to look the way they do. With new missions, new instruments, and new technologies, we will continue to improve our knowledge of the Moon and better understand the history of our solar system.
Only because high thorium concentrations where there's creep. I thought it was too much to put that at the main. There's a creep chart. So, any questions before we conclude? Let everybody go. Oh, I should have my going once, going twice. Yes, question.
Gravity on Earth is variable as the gravity on the Moon?
Okay.
Like that NASA showed?
Is the gravity on the Earth as variable as it is on the Moon? Well, first of all, that lunar gravity, it was a little bit deceptive because what we're measuring, that whole scale was 1 GAL, was an gravitational acceleration of 1 centimeter per second squared, and that was in like thousands of units of that. A milli GAL, it was 1,000 milli GALs equals 1 GAL. But even though it looked like a lot of different colors, but the differences weren't that great in total. But you're right, even on the Earth, I mentioned the average is 9.8 meters per second squared, and I think the number varies between about 9.7 something and 9.9, so it's pretty tight. But it's not always 9.8 exactly or 9.81. It varies a little bit depending upon whether you're on Mount Everest, the bottom of the oceans, where you are. It isn't significant, but it's measurable. Okay. Another question. Grace. Oh yeah, Grace did it for the Earth. Yeah.
Yeah, they did the same thing for the Earth called the gravity recovery and climate explorer. So Grace took that up. They have the same kind of
Well, yeah, the gentleman had mentioned the Grace, and actually, if you want, I have a chart of that. I'll show you. I have a chart of everything. Let me show you the chart because it's kind of cool. I gotta find it here. Oh, come on. Why is this not moving? Oopsie daisy. What'd JD do? Okay, let me find the... Oh, darn. Oh, just a second. My computer must be tired. Okay, so let me see. It's right next to the one... I think it's right here. Aha. So, I have 2 of them. I'm going to actually, I'm going to unskip them. So here's the one, as the gentleman mentioned, was with Grace. So now this is a little bit different. This is the GALs again, okay? GAL is 1 centimeter per second squared, but these are measuring milligals, which is 1,000th of that. So this is 51 thousandths, which is what, 5%? That's a 5% change over that, I believe, not even that. Anyway, you can see here that these are field anomalies. You have a higher in the Andes and for some reason down here in Southeast Asia. And the oceans, the gravity is less in the Atlantic especially. So that was the result of Grace. And the next one, this is Grace, the South Pole. I don't have much information on it. It's kind of a cool photograph, but I don't have what the scaling is. But you're right, Grace did the same thing as Grail. I'm not too sure. Grace must have meant gravity, research, anomaly. Okay, here you got it. Wow, okay. Okay, any other questions before we break up? Yes?
And this is an elementary class, you
Because, that's a good question. How do we know that a rock that fell in Africa came from the moon? Because, pardon? Well, no, there are some things they see fall. But, even if you saw it fall, you'd have to triangulate on that meteor to see, to figure out where it came from in the orbit and did it come from the moon or Mars. But for the most part, what they do, they've been to the moon, they know what the rocks are like, they know the composition. For the most part, they're very similar to the Earth in terms of isotopes. But there are some differences that they can tell, and are they going to be 100% accurate all the time? Maybe not. It's a little bit, Mars is a little bit easier because, they know that Mars has a very subtle atmosphere, right? And when they get into a meteor or meteorite that's on the Earth, and they can see that, oh my gosh, this has the same, atmosphere, albeit they have 1/100th the atmosphere on Mars than we do, but they can measure it and they say, this has to come from Mars because it has the same atmosphere that we understand, because we know what the atmosphere on Mars is. We've been there, done that, we've collected it. Moon's a little bit tougher because there's no atmosphere. But still, we have a pretty good idea. We have 800 pounds of rocks from Apollo, and then the Russians picked up about 10 ounces back in the 70s, and then China picked up 4 pounds of rocks. So they got a pretty good idea of the chemical composition. Yeah. Any other questions? With that, I got some lunar rocks in the trunk I'm going to sell. Okay, no. Trust me, they're from the moon. Okay. Okay. And JD left.
Oh, thanks.
Oh, sure thing. Sure thing. Yeah. Yeah, these aren't very comfortable. I have a more comfortable position standing up.
Yeah, I think you did.
So I have a question. So couldn't they take from the South Pole and look at that gravitational
Difference anomaly, yeah.
difference anomaly, and couldn't they extrapolate from that and try and calculate the size of whatever that thing is?
Well, they have. That's
Oh,
why.
they have.
Well, that's why the one person said size of Denmark, and the other one said the size of 5 big islands. So they have made they have made an estimate, which is, I don't want to call it a guess. It's an educated guess, which is, but they've got a, yeah. They know something is there.
Right.
And for starters, they know something must have caused that large crater, if you will, at Mare. And then it's only a matter of looking at the difference in terms of the gravitational field and all that. Yeah.
Okay, I have a second question. On the near side of the moon, where everyone feels like the crust is thinner, could it be that because of that 7,000 degree Earth heating it up, that it caused some of those mares to actually even occur in the first place? That it was just causing the bubbling of the crust of the Earth and causing all that basalt activity to occur there? Or is
Well, that's possible, but the only issue is they have actually, through the sampling of the Mare, because they've taken, they can take those rocks, they can age them,
right?
and
They're younger
they're going to be younger because they're pretty sure that the moon thing happened, about 4.5 right after the Earth was formed, 4.5, 4.4 billion years ago, whereas the Mare vary in ages, and nothing's quite that old. Yeah.
Thank you very much.
Oh, sure thing. Okay, sure thing. Glad you enjoyed it. Yeah. Hey.
Thank you for the talk. I just wanted to make sure I didn't upset you at all when I switched. I told you about the.
No, not at all.
Okay.
No.
I messed up. I got Hill mixed up with Roche. So
Oh yeah, and I knew. I forget. Yeah, JD said it's Roche. Oh, that's right. No, that's fine. No.
I hope that what didn't come out was like rude.
No, not at all. No, you need to talk back and forth, and if I say something wrong or someone disagrees, oh, yeah, that's fine. Yeah, my gosh, that's no problem.
Yeah. I just wanted to make sure I didn't.
No.
But then on a great talk.
Okay. Well, thanks. Yeah. No, you're fine. You're fine. That's great. Yeah. Okay.
So wait, I had one question about, and I didn't want to blurt out a question, but so when you were talking about the lava rocks before, the ones that were explosive and the ones weren't explosive. You had two labels on the left and right, and I don't remember names of them exactly. It was the plot where it was the silicon content, and then it was like it determined whether it was explosive, magma, or lava,
Okay.
or solder. And I don't understand what those labels meant.
Let me see. Oh, no, that's fine. Let's see. Because they're pretty close there. I don't know, this isn't really moving very well. I don't know. Right here. So is the first one or second one? Was it this one right here?
Yeah, the Felsic and
Mafic?
Not,
Okay. I should explain that. So what it is, felsic, that means felspar, felspar. That's telling you these are felspars, orthoclast and plagioclast. So the felsic means it's a rock that's more felspar. Mafic, think of the M and the A the M as being Ma being magnesium, and the F is iron. So a mafic rock is one that has magnesium and iron, and a felsic rock is one that has felspar, like orthoclast and plagioclast. Yeah, that's what that is.
Okay.
But that's a good point. Those are such a big words there. I should have brought that up. Yeah.
Yeah, no, I was just wondering.
Yep.
So is it? So Malfic rocks are non-explosive, and
Well-
Felsic rocks are explosive per se.
Kind of works that way because the mafic, like basalt, is not explosive. I mean, you have the fire fountains and Kauai, but those are basically no more than the low 50% silica. So that's mafic. So whereas above 55, andesite, rhyolite, those are explosive. So those are more than 55. So you're right. It kind of falls in the category of mafic is not explosive and felsic is. You're right.
Okay.
Yeah. Yep.
Cool.
I never thought about that association. These fall under the non-explosive and these fall under explosive. They call it effusive. It's effusive because they basically, like not quite like running water, but the basalt just lava flows down, and it can run you over and burn you, but you can probably outrun it, right? You can't outrun some of these explosive things, right?
No.
Yeah, if you've ever seen the movie Dante's Peak, ever seen that movie?
I haven't. I heard the name.
Oh, it's a good movie. It's supposed to. I was told by a volcanologist one time it's probably one of the most realistic films about volcanoes. So yeah, Dante's Peak. Take a look at that sometime. Yeah.
Thank you.
Okay, sure thing.
Very interesting talk.
Oh,
Thank you so much.
yeah. Glad you enjoyed it.
Yeah, every now and then. Next event will be the 29th of April. Well, we'll probably do it again in April.
29th of April. We're going on the 28th.
Or not in April.
We're leaving.
Yeah, 28th.
We're leaving.
Yeah. So JD, what do you want to do?
Go to the first slide.
Okay. Okay. Bye. Hey, thanks, Bill and Connie.
Hey, good to see you again.
Go to the first slide. Okay.
Right. Good to see you. Yeah. How have you been doing?
Pretty good. Just lots of clouds this week.
All right.
But I'm doing pretty well here.
We've gotten real thin around here. Well, a lot of people have retired. Aubrey retired. Dan retired.
He wants to do some of these charts. I don't know.
Got to that age, so they retired.
No, they retired, but you
Hmm?
can
That's the problem.
Budget. Okay.
Okay.
You want to go through each one?
Yeah. Go through each one. Give a little pause. Then go to the next one.
Don't say anything. Just go through them.
Yeah. Well, you can say anything you want.
I think they like Moonraker.
Yeah. Well, they should. It's an awesome movie.
Yeah.
And yeah. And so you want to give a pause between any animations. The idea is that I've got a video of all the slides.
Oh, okay.
Then I can stretch out
Okay.
as needed. If it's a still, I can, just stretch it out as much as needed.
I hope I didn't get these out of the wrong out of order.
Beautiful. That was really great.
Oh, good.
Yeah, I think people quite liked it. We had
I think I did a pretty good job.
people here live, and we had
How many online?
13 was the peak, total of 22 last I looked.
Oh, okay. Well, 19 and 13. So 32.
32.
Yeah.
22 total views, average view time 32 minutes. So
So they didn't.
I would actually stick with the 22.
So they didn't hang around long online.
Yeah, was it 22?
What happened? I think a few did, which is fine.
So yeah, 30 views on total views with average view time just under 30 minutes.
So,
that's impressive.
but average view time, they leave after 30 minutes, the average person?
Yeah.
What?
So some people will jump in, look at it for a minute or two, and then jump out.
Okay.
But you know, when you're talking about 30 minutes, I think you count each of those as a view, because that's a considerable amount of time. So it was very well received. I think it was very well received for being our first one back.
Oh yeah, that's good.
Excellent. And the comment on YouTube, I figured out it was the user's name is Slams Dunk, and he had like a moon icon. That was his comment.
Oh.
Yeah, it's someone from Maui because his pictures looked like someone from Maui.
So he didn't say the talk was a slam dunk. His name was Slam Dunk.
Yes, SLAMC. So, kind of cool. I would still take it as a positive.
Oh yeah.
And you already have one like, which is kind of
One like.
which is certainly not bad.
Yeah.
Oh, and Dr. Gary Greenberg, Gary,
Yeah, I know who he is. Yeah.
you remember his?
Yeah.
He has pictures of moon dust.
Oh, okay.
Maybe we ought to get you in touch with Gary, if you would be interested.
Oh yeah. Oh yes, moon dust. Okay.
Yeah. That's a great idea.
Well, you had a lot of stuff in here. So a lot of different things. Yes.
Right. Yeah, it was really great. Very nice. And with the delay, I got to listen to it twice. Once with my left ear and once with my right ear. Okay. Oh. Okay, I'll try to remember to put in the glass breaking sound. Because that is classic. That is.
Nothing spells break like breaking glass, right?
Yeah, exactly.
And played the whole movie here?
No, I might actually edit out the movies.
Oh, okay.
Because, yeah.
I mean, yeah, a movie or whatever it is.
Yeah. Right.
So just stop that then? Not
So just
continue?
go on, yeah, go ahead and go on to the next one. Thank you for doing this.
Oh, sure, I enjoy it, JD. Yeah.
Hoping that this will make, well, Thank you for the whole talk, but thank you for doing this as well. I'm hoping this will make it
Oh, yeah.
easy for me to put together a video. I will edit out things if I'm a little worried about
Okay.
copyright, like the videos. I think we'd be pushing it. NASA. Well, no, NASA might not.
Well, yeah, a lot of them.
We know from decades of study that the moon has water. But where and
So
how much?
just keep
In
keep going on that.
2024,
Or?
a robotic rover will explore the moon's surface in search of water
Find that
ice.
online.
NASA's Viper
I'm
moon
pretty
rover
sure
will
it's
perform the first
YouTube.
resource mapping mission on
Interesting, a gentleman back there, I guess, worked on Grace.
He worked on the laser ranging station.
Oh, okay. But he was aware of Grace. I had a chart on Grace, yeah.
That's Dan O'Gara.
Okay.
So yeah, anything laser ranging, he would be a good person to talk to.
And the gentleman straight in the back that works here, right? What was his name? That was.
The right corner. Yeah, the big guy, really.
Well, no,
tall
the
guy.
one at the computer back there.
Oh yes. Hayden.
Hayden, yeah, Hayden. Okay, he works here, yeah.
Yeah, he works here. He's the computer guy for PanStars.
Oh, for PanStars. Okay,
Yes.
okay.
Yeah. So, I know he was working here before Safan left, but he's kind of the Safan.
Well, I still show this, even though I didn't show. I only pulled it up to show that gentleman.
Okay.
But it
No worries.
wasn't part of the talk. Only because I wanted to restrict my number of charts.
It's easy to edit out. Let's put it
Okay.
that way.
We can keep it in, but
Yeah.
it just wasn't part of the talk.
Right. Right. Yeah, I would have to grab the audio from the end and weave it in somehow. I might do it. I don't know. Let's see how it looks.
And you don't want that movie either, right?
If
See-
I need it, I'll go find it.
Okay. Yeah, this is actually part of. It's from NASA's Goddard Space Flight Center
Yeah.
and USGS.
Yeah. And if I do go get it, I can look at what their
Okay.
use policy is. Some people do have. I mean, there's a lot of video I found out there that they're like, go ahead and use it, just to
Yeah.
tell everyone who I am.
Yeah.
It's like, okay. Oh, and I didn't, I'll go back and listen to it. What was the final answer on how do they know it's from the moon?
Well, because they've got 800 pounds of lunar material, so they know the composition, and they can pretty much tell the composition of even though it's very similar to Earth. Yeah.
Chemical composition.
Yeah, yeah.
basically, yeah. Okay. Sounds good.
It's interesting. One young man, I went back. He didn't ask me. He should have asked me during the class. He asked me what mafic and melsic was. So I mentioned, well, melsic, that stuff on that side is feldspar. What it is it's feldspar-ish. So it's felsic. So felsic falls in this area where orthoclase is feldspar, plagioclase is feldspar, mafic. The M and the A stand for magnesium and the F for iron. So if it's a mafic rock, it has olivine, pyroxene, it's got lots of iron and magnesium. Yeah.
Okay.
And I never made the connection before, but he said, so since I said basalt up there was effusive and not explosive, he said, does that mean all mafic rocks are going to be non-explosive? I said, well, Yeah, they're probably right because it falls in that category. Whereas andesite over to rhyolite falls above like 55% silica, so those are more explosive, and those are primarily felsic. So that was an interesting insight. And I said, gee, I wish you would have asked me that question during the class. But
During the lecture,
yeah, it's class, lecture, not a class.
Talk, that's it. Let's go for talk.
Talk,
Yeah.
presentation.
Presentation, that's good, yeah.
I actually got that book there.
Yeah.
I haven't had much time to look at it, but I think I have that one too. I haven't had much time to look at it.
I think there's a book or two about the moon around here, but they're older than I am. Might be older than you are. They're,
Oh,
you
yeah.
know, yeah, they've been around for a while.
And nobody knew, I stumped them. Nobody knew Henry Wadsworth Longfellow.
Yeah, no, I didn't get it either, so.
And then the LRO, it's a 4-minute video.
Yeah.
And I didn't have that one in class. I just happened to, it was at the end. Okay.
Okay.
So that,
That's
okay.
that should do quite nicely. Okay. And I will stop streaming now.
Okie doke. Go ahead. Load